Hello students, welcome back to Basic Electronics subject from VTU. This is the fourth video of module 1. In the earlier video we have discussed bandwidth. Now let us continue with the bandwidth. Bandwidth is nothing but the range of frequencies where the gain is almost constant. How do we find out this gain? For example, if this is the frequency response, on the x-axis we have taken the frequency, and the y-axis it is the voltage gain. So this constant gain we call it as a mid-band voltage gain. So if it is voltage gain, what we have learnt is voltage gain AV max by root 2 will give you 24.7 or 0.707 into 35, 0.707 of the maximum gain, or 70.7% of the mid-band gain. Here you will get the mid-band gain by root 2. So here it intersects, so let us call it as the lower cutoff frequency. Here it intersects, we call it as the upper cutoff frequency. The difference between these two frequencies, f2 minus f1, is nothing but the bandwidth. The bandwidth of an amplifier is usually taken as the difference between the upper and lower cutoff frequencies, f2 minus f1. The bandwidth of an amplifier must be sufficient to accommodate the range of frequencies present within the signal that is to be presented with. Many signals contain the harmonic components. That signal consists of the signals with the frequencies 2f, 3f, 4f, 5f, etc., where f is the fundamental frequency, or where f is the frequency of the fundamental signal. Now let us see what is phase shift. Phase shift is the phase angle between the input and the output signal voltages measured in degrees. Usually we say the phase difference between the input and the output signal is 0 degrees, 180 degrees or 360 degrees. So phase shift is the phase angle between the input and output signal voltages measured in always degrees. Where we measure this? The measurement is usually carried out in the mid-band, where for most amplifiers the phase shift remains relatively constant. For conventional single-stage transistor amplifiers, usually they provide 180 degree phase shift. What do you mean by 180 degree phase shift? If the signal is this one, let us assume the input signal is this one. If the output signal is something like this, so this is 0 degree, this is 180 degree, this is 360 degree, after which it repeats itself. Here the signal rises, but here signal C is falling, but here signal starts to rise. The difference between this, the phase angle between this and this is 180 degree. Phase angle between the input, if you assume this is the input, this is output, there is a 180 degree phase shift. Suppose if the output voltage waveform go like this, then what may be the phase shift? Here the output voltage waveform, green is our output, red is input. Let us consider this is 0 degree, this is 90 degree, this is 180 degree. Then we say there is a phase shift of 90 degrees. Now let us move on to the feedback. The feedback is nothing but some portion of the output is fed back as the input. So that is nothing but the feedback. So let us consider this as a basic amplifier. This is the block diagram of a basic amplifier whose gain is AV. A stands for gain, V stands for voltage gain. Usually the transistor amplifier provides a phase shift of 180 degrees. So this basic amplifier is providing 180 degree phase shift whose voltage gain is AV. The output voltage is V out if the input voltage to the basic amplifier is V in dash. This is the basic amplifier whose input is V in dash and output is V out. Some portion of the output is sampled by a feedback network whose feedback ratio is beta. Beta usually will be in the fractions 0.1, 0.2, 0.3, etc. Here there is a mistake in the prescribed textbook, in your VTU prescribed textbook. For the negative feedback, there will not be any phase shift. There will not be any phase shift. First of all, there are two types of feedback. One is positive feedback, the other one is negative feedback. If you're talking about the negative feedback, here the input signal, let us say the input signal is like this. Then the output signal will have 180 degree phase shift, Here is a positive half cycle of the input. Here is the positive half cycle of the feedback signal. Here the phase difference between these two signals is 180 degrees. So the amplifier here provides 180 degree phase shift. So no necessity of here phase shift of 180 degree. So there is a phase shift of 180 degrees. So this is the input signal. This is the feedback signal. So there is a phase shift of 180 degrees. So if the waveforms are like this, they does not aid each other, they oppose each other, or the feedback signal will get subtracted from the input signal. Input signal minus feedback signal. So the effective input to this amplifier, that is V in dash, will be less than the input, will be less than this V in. So input drops. If the input drops, the output also drops. So the voltage gain AV definitely reduces. So in the negative feedback, the voltage gain reduces. So I'll repeat, the feedback is nothing but a fraction of the output is sampled and applied as the input to an amplifier, then we say there is a feedback. There are two types of feedback, positive feedback and negative feedback. If the input signal and the output signal will not have any phase difference, we say the phase difference is 0 degree, or you can say phase difference of 360 degree. If there is no phase difference between this, they aid each other. The input signal will get added with the feedback signal. So the input, the effective input to the amplifier increases, output also increases, so gain also increases in the positive feedback. Coming to the negative feedback, if you assume this is the input signal, there is a 180 degree phase shift by a transistor amplifier, so the feedback signal looks like this. So these two things, they subtract each other, input V in minus the feedback signal. So effective input drops, output voltage also drops, so there is a drop in the gain also. So in the negative feedback, remember, gain will be reduced. In the positive feedback, the gain is increased. Many practical amplifiers use negative feedback in order to precisely control the gain. The advantages of negative feedback are the stability of the gain. Gain stability is important. Even though the gain drops in negative feedback, gain reduces, but due to the stability of the voltage gain, the negative feedback is used in amplifiers. Whenever you hear amplifiers, remember negative feedback. All amplifiers uses negative feedback. But also remember, amplifier is a circuit which increases the strength of a weak signal. Amplifier increases the strength of a weak signal, but it uses negative feedback where the gain reduces. But still, we use negative feedback in the amplifiers because there is a stability of the voltage gain. Stability is more important. The negative feedback also reduces the distortion and the bandwidth increases. Because of these advantages, negative feedback is more popular in amplifiers. The gain can be reduced to a manageable value by feeding back a small portion of the output, that is the feedback. The amount of feedback determines the overall gain. When there is a feedback, we say it is a closed loop network. When there is no feedback, if there is no feedback, then we say it is an open loop. Remember, when there is a feedback, it is closed loop. When there is no feedback, it is open loop. Negative feedback, always the overall gain decreases. Then coming to the positive feedback, here the output is fed back in such a way as to reinforce the input. That means the feedback signal aids the input. They add each other rather than subtraction. So we call it as a positive feedback where the gain increases. This form of feedback is used in oscillator circuits. Whenever you hear oscillator, remember positive feedback. But whenever you hear the amplifier, remember negative feedback. Let us come to the diagram. Let us come to the diagram of the negative feedback amplifier. As I said, there is a small mistake in the prescribed textbook. So I have taken the same diagram just to tell you that there is a mistake and you need to rectify in your textbook. So negative feedback, what we need is, this is the input. If this is the input, the feedback signal should be 180 degree out of phase. So basically this is the basic amplifier whose gain is AV. The phase shift is 180 degrees. Usually the transistor amplifier provides 180 degree phase shift. The basic input for this amplifier is V in dash. Observe the polarities. Here, because of the phase shift, 180 degree phase shift, see the polarities of the output voltage, here negative, here positive. This is a V out. Some portion of the output is fed back as the input. So that is decided by the feedback ratio beta. Here we don't need phase shift of 180 degree. Suppose if there is a phase shift of 180 degree, this 180 will get added with 180. 180 plus 180, 360. 360 degrees means there is no phase shift. Then it becomes positive feedback. So here there is a mistake in the prescribed book. So you are not supposed to write the feedback. Now totally in this loop, totally there is only 180 degree phase shift. If there is only 180 degree phase shift, you will get this feedback signal. So you can observe here, we have sampled the output. So here positive, here also positive. Here this is a negative terminal, here also negative. If there is no phase shift, here this is positive, this should be negative. There also there is a small mistake. Same terminal is connected here, so this should be positive, this should be negative. So these are the changes you should make in your textbook or in your notes. Now let us see what happens to V in dash. V in dash is the input to the amplifier. For the overall amplifier with feedback, the complete this block is called as the amplifier with feedback or closed loop network. If you consider this as a complete closed loop network, then the input is V in, then the output is V out. So overall gain G, if you complete overall gain G is given by the output V out divided by the input V in, V out by V in. What is this V in dash? Remember, this is negative feedback. In negative feedback, V in dash is equal to the input voltage V in minus the feedback voltage. Feedback voltage is beta V out. From where we got this beta out? Let us see this. So as you know, this is the input to the closed loop amplifier. V in dash is the input to the amplifier. Here is V out. The feedback ratio is beta. So output here becomes beta V out. Here the output becomes beta V out. So this beta out is the feedback voltage. If you observe, this is plus minus minus plus. Plus minus minus plus, they subtract each other. So here we have written V in dash is equal to V in minus beta out. Then rearrange the terms to get V in. V in is equal to V in dash minus beta V out. So this is one important equation because we need to substitute in this overall gain G. So we got it, the expression for V in. Then what is this V out? What is this V out? V out is equal to, this V out is equal to A into V in dash, A into V in dash. Output voltage is equal to gain times, here AV they have taken, so let us also take AV into V in dash. If you find problem with writing this, so it can be easily written as AV is equal to this voltage gain. AV is equal to output voltage V out divided by the input voltage of this amplifier, that is V in dash. So from this equation, definitely you can arrive at V out is equal to AV into V in dash. Now substitute this equation 1 and this equation 2 in this overall gain equation. The next slide, we will check it. The same thing, whatever I have explained here, V in dash is equal to V in dash. Remember, V in dash is the input voltage to the basic amplifier. So that is equal to input voltage to the closed loop amplifier, V in minus beta V naught, where beta V naught is the feedback voltage. So this you will get by applying the Kirchhoff's voltage law. Rearrange this equation, so you will get V in is equal to V in dash plus beta V out. So let us call this as equation 1. And V out is equal to AV into V in dash. Here also there is a mistake in the book. AV into V in dash. From where we got this? Voltage gain, open loop voltage gain. Open loop means when there is no feedback. AV is equal to V naught by V in dash. So let us call this as equation 2. Substitute equation 1 and 2 in the overall gain equation. G is equal to, overall gain equation is G is equal to V naught by V in. So V naught is equal to V in dash plus beta. V naught is equal to AV into V in dash, AV into V in dash, AV into V in dash. V in is equal to V in dash plus beta V out. Substitute equation 1 here, equation 2 here. So AV into V in dash divided by V in dash plus beta into substitute for V out from equation 2. Substitute for V out from equation 2. AV into V in dash. Rearrange these terms, take V in dash common, V in dash common. If you take V in dash common, 1 plus beta AV, 1 plus beta AV, V in dash gets cancelled. So finally you will get the overall gain G is equal to AV divided by 1 plus beta AV. This is the important gain equation of the negative feedback. Hence, the overall gain with negative feedback applied will be less than the gain without feedback. Always with the negative feedback, the gain reduces. Without feedback, the gain will be more. Further, in this equation, let us assume AV is much greater than 1. AV is much greater than 1. If AV is very large, observe the equation AV divided by 1 plus beta AV. 1 plus, we are assuming AV of very large values. So that multiplied by beta definitely will be greater than 1. So you can neglect the 1 if AV is much greater than 1. So then this equation 3 can be written as G is equal to, if you neglect 1, it becomes beta AV. If AV is very large, you can neglect this 1. So AV gets cancelled. So G is equal to 1 by beta. The overall gain of the negative feedback amplifier will depend on the feedback network only when AV is very large. Also, the product of AV and beta, AV and beta is called as the loop gain. Loop gain of a feedback amplifier is defined as the product of AV and beta. Why AV and beta is called as the loop gain? Here this is the loop. Here is the amplifier network. This is the feedback network. Here the gain is AV. Here the feedback ratio is beta. So product of this definitely will give you the loop gain. The loop gain is nothing but beta AV. Here is an example, very simple example, just a LKG problem. So let us go through this. An amplifier with negative feedback applied has an open loop voltage gain of 50. Open loop voltage gain of 50. Open loop voltage gain. So AV is equal to 50. And 1/10 of its output is fed back to the input. 1/10 of the output is fed back to the input, that is beta. The feedback ratio is 0.1. Determine the overall voltage gain. Overall voltage gain of a negative feedback is given by G is equal to AV divided by 1 plus beta AV. AV is given, beta is given, just to substitute, you will get the value 8.33. Same example, continuing with that, the amplifier's open loop voltage gain increases by 20%. The amplifier's open loop voltage gain was 50. Now he is saying increase that voltage gain by 20%. Determine the percentage increase in overall voltage gain. First let us calculate this 20% hike. AV is equal to AV plus 0.2 into AV. 20% increases. So 50 plus 0.2 into 50. So totally you will get it as 60. The overall voltage gain with negative feedback will then be G is equal to AV divided by 1 plus beta AV. Now the AV has increased by 20%. So 60 divided by 1 plus 0.1 into 60. Check this value. I don't think you will get 7.14. I think you will get it as 8.57. Check using your calculator. So the increase in the overall voltage gain, is expressed as a percentage. So this is 8.57. Once again, the mistake in your textbook. 8.57. Change in your textbook. So the increase in the overall voltage gain expressed as a percentage will thus be 8.57 minus 8.33 divided by 8.33 into 100%. Usually we want to express this as a percentage, so we have multiplied with 100% because we need to find out the percentage increase in the overall gain. So if you calculate, you will get it as 2.88%. If the voltage gain, the open loop voltage gain increases by 20%, if the open loop voltage gain increases by 20%, see the overall voltage gain change. The overall voltage gain just changes by 2.88%. So I said in the negative feedback amplifiers, the voltage gain is very much stable. 20% hike in the open loop voltage gain, but overall voltage gain increases only by 2.88%. An integrated circuit that produces an open loop gain of 100 is to be used as a basis of an amplifier stage having a precise voltage gain of 20. Determine the amount of feedback required. Just determine the amount of feedback required. So G is equal to AV into 1 plus A beta. AV beta is nothing but the overall gain equation. So the values are given here. Open loop voltage gain is 100, having a precise voltage gain of 20. So overall voltage gain is 20. So in this equation there are three terms. So G is given, AV is given, just we need to determine beta. So substitute and play with the T equation, definitely will get the value of beta as 0.04. As you know, the negative feedback amplifiers reduces the overall voltage gain. But amplifier is a circuit which increases the strength of a weak signal. We need large amounts of gain. In order to provide sufficiently large values of gain, usually we use number of interconnect stages within an amplifier. Within an amplifier, we will have different stages. Within an amplifier, we will have different stages. They are interconnected. Stage 1, stage 2, stage 3. So this will be multi-stage amplifier. Within that, we will have different stages of amplifier. Then what will be the overall voltage gain of this? Suppose if the first stage is having a voltage gain of AV1, second stage is having AV2, third stage is having a voltage gain of AV3, then overall voltage gain is given by the product of the voltage gain of the individual amplifiers. So AV is given by AV1 into AV2 into AV3 into etc. etc. It depends on the number of stages. Like this, we can increase the overall voltage gain. An increase in the gain can only be achieved at the expense of the reduction in the bandwidth. Let us see what are the different types of multi-stage amplifiers or different methods used for interstage coupling. Coupling means how we connect the two stages of amplifiers. Let us say this is stage 1 amplifier, this is stage 2 amplifier. How we are going to connect these two stages is nothing but the coupling. Now the first method of coupling, you can see here the typical RC coupling between the stages. Here is the first stage of an amplifier, here is the second stage of the amplifier. We want to couple these two stages. So here the coupling is done by RC, resistance, capacitance. So here is R, here is C. By using this RC coupling, we can avoid the DC voltages of the first stage transferring to second stage. So DC voltages are avoided. The most commonly used method is the RC coupling. In this coupling, the stages are coupled together using capacitors having low reactance at the signal frequency and resistance. One more type is LC coupling. LC coupling. Here is an inductance, here is a capacitance. In this method, the inductors have a high reactance at the signal frequency. Let us go to the third different method. A transformer coupling between the stages. Between these two stages are connected via a transformer. This type of coupling generally used only in RF and high frequency amplifiers. So in RF and high frequency amplifiers, this transformer coupling is used. Then here it is a direct coupling. There is no transformer, there is no LC, there is no RC. Direct coupling. Directly we are coupling these two stages. In this stage, the DC values are transferred to the second stage. The DC levels present on signals must be preserved. When you want to preserve the DC values present on the signals, we go for direct coupling.